Equipotential surface is any surface that has same electric potential at every point on it is called an equipotential surface. Equipotential surface on which every point have same value of electric potential. Now we discuss some important properties of equipotential surface. First, no work is done in moving a test charge over an equipotential surface. Let A and B 2 points over an equipotential surface whose electric potential is what? V. So in this condition a test charge Q is moved from A to B, then work done WAB equal to Q VB minus VA, but it is equipotential, so VB equal to VA equal to V constant, so WAB equal to 0, means no work will be done for moving a test charge on equipotential surface. Now second important property, electric field is always normal to the equipotential surface, means electric field is always perpendicular at 90 degree to the equipotential surface at every point. We know that work done by moving charge Q from A to B, WAB equal to 0 as we discussed earlier, but by the definition W equal to F dot dl, but force on Q, F equal to QE, W equal to QE dot dl, QE dl cos theta. From 1 and 2, WAB equal to 0, so QE dl cos theta equal to 0, but Q is not equal to 0, electric field is also not equal to 0, displacement is also not equal to 0, so cos theta equal to 0, so theta equal to what? 90 degree. Thus for any charge configuration, equipotential surface through a point is normal to the electric field at that point. No two equipotential surfaces can intersect each other at any point. If they intersect each other at a point, then we get two electric potential at a point, which is not possible. Fourth point, equipotential surfaces are closer together in the region of strong field and farther apart in the region of weak field. We will get a relation between E and V as E equal to minus dV upon dr. This one we will discuss in next topic. So for the same change in value of dV, if dV is constant, then what we get? E proportional to 1 upon dr. So if dr is less, electric field is what? Most. The spacing between the equipotential surface will be smaller in the region where electric field is stronger, and vice versa, means if space between equipotential surface is more, then electric field will be less. Equipotential surface of various charge system. First one, equipotential surface of a positive point charge. Electric potential due to a point charge Q at a distance r. From it is given by V equal to 1 upon 4 pi epsilon 0 Q upon r. If r is constant, then V equal to constant. Thus, equipotential surface of a single point charge are concentric spherical surface center at the center. Here we can see at the center one charge Q is there. Equipotential surface R 1, 2, 3, 4, 5 having different radius. So due to the single point charge, equipotential surfaces are spherical surfaces which having the same center. Second, equipotential surface for a uniform electric field. The line of forces are parallel, straight line R, and equipotential surface are equidistant from equidistant parallel planes perpendicular to the line of force. Here in this diagram we can see that the electric field lines are what? Parallel to each other, and here we can see 1, 2 and 3. These equipotential surface are at equidistance from each other. Potential surface due to electric dipole. As you know, electric dipole is just a pair of two equal and opposite charge. So from the figure we notice that the electric potential surfaces, here we can see this dash 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 lines represent the equipotential surface due to electric dipole. Very important from this diagram, here we can see here between the two plates, between the two charges, we notice that they are close together in the region in between the two charges. Here they are closer, but apart from in this direction they are far apart. Equipotential surface of two equal positive charges. From figure we notice that they are far apart in the region in between the two charges, indicating a weak field in such region. Here you can see they are far apart. Compare with the previous case where they are crowded, they are nearer to each other. Just opposite to this one, they are here they are apart, but here are what, they are closer. Last very important relation between field and electric potential. Here we consider two equipotential surface A and B. Equipotential electric potential of surface A is what, V, and B is what, V plus delta V. Electric field from A to B is in this direction E. We consider a point P on equipotential surface B. Okay, so let P be a point on the surface B, and delta L is the perpendicular distance of surface A to point P. The work done to move a unit positive charge from the surface B to surface A against electric field. The work done in this process, WPR equal to E delta L, but W equal to P delta VR minus VP. VR is what? V minus V plus delta V equal to minus delta V. From 1 and 2 we get E equal to minus delta V. Since delta V is negative, H electric field in decreasing electric potential direction. So in this condition delta V is what? Negative. So E equal to minus delta V dl, or E equal to plus delta V upon dl. We can write this relation in other form as E equal to minus dV upon dr, or in form of magnitude E equal to V upon d. Important conclusion of this relation: electric field is in the direction in which potential decrease is steepest. Its magnitude is given by the change in magnitude of potential per unit displacement perpendicular to the equipotential surface at the point.